So let's move forward, and in this lecture we will learn one new type of numbers which are very unique in nature. This is pyramids, and every one of you know that it was built a very long time back. Pyramids from a structural point of view itself is a wonder. Though we don't see pyramids very often in nature, we know that there is a lot of symmetry associated with pyramids. And especially these Egyptian pyramids have always fascinated people, right? When you think of the country Egypt, the first thing that comes to your mind will be pyramids. And pyramids have some connection to what we are learning today. So let us ask all of us some questions like, can you think of a number that cannot be written as a simple fraction? So in all your previous lectures, we learned about rational numbers, that numbers that can be represented as p by q, where both p and q are integers and q not equal to 0. So rational number we were always able to represent as a simple fraction. Now can we think of a number that cannot be written as a simple fraction? Now if such numbers exist, then what do we call those numbers? And can we find examples of such kind of numbers in nature or in daily life, or as you can see in this picture in pyramids? We will see in this lecture. So whatever we are going to learn today, understand that humans have found about these numbers long time back. Egyptians knew about these numbers way back around 2500 BC, roughly like almost 4500 years ago. We knew about these kind of numbers. And not just Egyptians, even Greeks too knew about these numbers. Okay, they were well aware about properties of these numbers and how these numbers can be utilized to build structures which are aesthetically, geometrically pleasant, unique and perfect. And many more people knew about this. So it is not just Egyptians or Greeks, many more people knew about this. And soon all of you will know about these numbers. So through our practice of solving examples and problems, we understood that between any two rational numbers, there are infinite numbers available, right? So we have done plenty of examples where we were asked to find some certain number of rational numbers between any two rational numbers, and we had two methods for finding it. Let us look at a number line, and now we will ask a question, that is, are all the numbers between any two rational numbers a rational number? For example, let's pick two numbers 1 and 2. Okay, between 1 and 2, let's say we were asked about a question that we have to find. Let's say we have to find infinite amount of numbers between 1 and 2. Okay, let's say we built a computer that is capable of calculating infinite amount of rational numbers between 1 and 2. So we program it and we let that computer do the calculation, and it will output infinite rational numbers between 1 and 2. Now, will there be any number between 1 and 2 which this computer cannot calculate according to the algorithm that we have built into? That is a question. That is, are all the numbers between the two rational numbers here 1 and 2? So 1 can be written as 1 by 1, 2 can be written as 2 by 2, and we have built a computer to find, based on the two methods that we have discussed before, we built an algorithm and the computer is going to output all the numbers between 1 and 2. Now the question is that, are all the numbers between any two rational numbers a rational number? Of course, yes, the program has been built in such a way that it will output a rational number. But after the computer outputs all the numbers, so it is not going to end, it's an infinite process. But still, when we think of the capability of such kind of a computer, will there be any number left that we are yet to find between 1 and 2? Or does a number exist between 1 and 2 that this computer cannot find? And the ultimate truth is that there are numbers between any two numbers or any two rational numbers that are not rational numbers. And you can imagine that it is not logically very acceptable, right? What is the literal meaning of rational? Rational means there is some logic behind it, right? And what I have just said now is that there are numbers between any two rational numbers that are not a rational number, right? So it is not rationally sensible, or it is not logically acceptable for our human brain, right? But the truth is that you pick any 2 points in the number line, there are numbers which are not rationally sensible. Okay, so they are far more than what we can imagine actually, right? It is in a way it is far more than what we can imagine about it. So to solve this mystery, what we do is that we'll give numbers a very fresh look. Okay, whatever we have learned till now about the numbers and the types of numbers, let us look numbers from a very new perspective and try to see the gaps that we have left out, or can we build new meanings from whatever we have learned till now. We will look at how some numbers behave when we make a fractional number into a decimal form. What we do now is that we take several kinds of fractions and we make a division and convert it to the decimal form. Let's start with a fraction 21 by 4. 21 by 4. Let us convert this into decimal form. How can we do this? We can do the division process. So 21 divided by 4, I can do into 5, 20, remainder is 1, 2, I'll get 8, remainder is 2, I can do 5, I'll get 20, and now 0 remainder. So the answer is 21 by 4 is equal to 5.25. Perfect. Let's do one more example. 21 by 5. I can do 21, 5 into 4, 20, remainder is 1, and I will get into 2, 10, 0 is a remainder. Therefore 21 by 5 is nothing but 4.2. Another example, 10 by 3. How much will this come to be? So 10, 3 into 3, I get 9, 1 as a remainder. Okay, again 3, 9, 1 as a remainder. Again 3, 9, 1 as a remainder. Again 3, 9, 1 as a reminder. And by now you know that this is not going to end. This will continuously go on forever, and this particular value, it will continuously increase. Therefore 10 by 3 we get as 3.33333 and so on. Let's try one more example. 1 by 7. So let's do 1 by 7. So it's going to be 0. I get 1 as a reminder. I can do 1 here. I'll get 7 here. 3 as a reminder. I can do 4. I will get 28. I get 2 as a reminder. I can do 2. I get 14. I'll get 6 as a reminder. You multiply by 8. 56. I get 4 as a reminder. I can do 5. 35. 5 as a reminder. I can do 7. Get 49. I have 1 as a reminder. I can do 1. I get 7. I'll get 3 as a reminder. And continue. I'll get 0. I can do 4. I get 28 as a reminder. I get 2. We got 1 as a reminder here, and the same reminder we got here, 1. Okay. And in the next step we got 3 as a reminder, and we got the same 3. So the reminders have now become repeating. For 1 by 7 we got 0.142857, and then again it is repeating. And if you continue this process, you will get 142857, and then again 142857, 2.857 and so on. Therefore 1 by 7 is equal to 0.142857, again 14287, again 14287, and then so on. So we can see that we have one set, okay, and then we have another set, and then we have another set which is repeating. In summary, we now have two observations. One is, when we look at numbers like 21 by 4 or 21 by 5, we got a decimal form which is in a way complete. And when we looked at fractions like 10 by 3, again we were able to make into decimal form, but it was never ending, and at the same time it was continuously repeating with the same value. Same here for 1 by 7, we got again the decimal form in repeating fashion, but here we have a block of numbers, and that block of numbers was continuously getting repeated. In summary, we can make the following observations. Number 1, some fractions like 21 by 4, 21 by 5, it resulted in a decimal form like here, okay, which is in a terminated fashion. That means it is exactly 5.25. There is no ambiguity or confusion whether it is 5.25 or something beyond or not. Similarly, 4.2, it is absolute and complete. Resulted in a decimal form and it terminated. It terminated meaning the decimal form is complete. And the second observation is that some fractions resulted in a decimal form, but it did not terminate and it kept repeating. That means in the case of 10 by 3, we got a decimal form, right? Again, in the case of 1 by 7, we got a decimal form, but it did not end. It is continuously going forever, or it means that it did not terminate, or it is non-terminating. But we got a decimal form. Again, same case for 1 by 7, we got a decimal form, perfect, but it did not end. It will go on forever. We got a decimal form, but it is not going to end. It will go on forever. So in summary, we make the following observations. Okay. First thing is that some fractions results in a decimal form and it is terminated, right? Like the way we saw for 21 by 4, it came out to be 5.25, and then we saw 21 by 5 comes to be 4.2, so it is a perfectly terminated decimal. And we saw that some fractions results in a decimal form and it did not terminate but kept repeating, right? This we saw for the example 10 by 3, where we got 3.3333 and it doesn't end. And we saw one more example 1 by 7, where we saw a block of numbers repeating itself, right? So this for 1 by 7 we saw 0.142857, and this 142857 it kept repeating. Okay, I'm just highlighting it with different colors, but it will go on forever. So now we will now think of some questions. Okay, so what are those questions? First one, is it possible to convert all fractions into their decimal equivalents, right? Just now we took some fractions or rational numbers and then we converted into the decimal equivalents, and then we saw that okay, it can either terminate or it could be non-terminating repeating. Like another example 10 by 8, we got 1.25. Here we are converting a fraction, that is 10 by 8, into a decimal equivalent, which is 1.25. So is it possible to do this for all the fractions? Okay, that's the first question. Second, how can fractions in decimal form either terminate or be non-terminating but repeating? right? That is, let's say in the case of 39 by 5, we got 7.8, and when we do 39 by 7, that is a different divisor, we get a non-terminating but repeating decimal number. Now, the question is that how can fractions like 39 by 5 or 39 by 7 end up into a decimal form like 7.8 or 0.57 and so on? What is the underlying reason, or how these fractions end up being a terminating form or a non-terminating repeating form? Is there a way that we can predict it or estimate it? Okay, that's the second question. And then, is there a decimal number that is neither terminating nor repeating? We now saw a few decimal numbers which are either terminating or it is non-terminating repeating. Now, can we think of a decimal number? It doesn't terminate and it doesn't repeat. Let's say you look at this particular decimal number 4.358898944. So, this is not terminating, okay? It is going on forever. And one more thing is that it doesn't repeat, unlike this particular decimal number where a block of numbers are getting repeated. Here there is no block of numbers getting repeated, so every number that is coming up next is a unique one, and at the same time it is going on forever. Okay, and last, one more question that we can ask is, can we transform all decimals into a fractional form? Up until now, what we were doing, we took a fraction right here and then we converted into a decimal form. Okay, and then we found out all this behavior. Now let us flip the situation or reverse the situation. That is, we take a decimal number and can we convert it to a rational form? And can we do this for any kind of decimal number? That is, can we transform all decimal? So any kind of decimal number you think of, can we transform it to a fractional form, right? For example, let's think of a number like 2.1111. Okay, 1 is going on forever. This decimal I can transform it as 19 by 9. Okay, that is, I convert a decimal number into a fractional form. Now the question is that, can we transform all the decimals? So any kind of decimal I take, can I do this transformation to a fractional form? That is a question. We will now answer all this 4 questions one by one. So let us look at the first question. Is it possible to convert all fractions into their decimal equivalents? And the answer is yes. We can convert any fraction into their decimal equivalents. But there will be 2 kinds of behavior that we can expect. That is, it can either terminate or it can be non-terminating but repeating. So again, we can transform or convert all the fractions into their decimal equivalents, but it will be of either 2 types. Either it will terminate or it will be non-terminating but repeating. Second question, how can fractions in decimal form either terminate or be non-terminating but repeating? So let us consider a rational number p by q, and it is in its simplest form. Okay, that means p and q are now coprime. Now, if the denominator, that is q, we are talking about q, if the denominator only contains 2 and or 5, if I represent q in its prime factorized form and it contains only 2 and 5, that is 2 to the power of some number a multiplied by 5 to the power some number b. So the denominator can contain either 2 or 5 or together. Okay, in such scenarios, what happens? This fraction will terminate. The decimal form of these fractions will terminate. And second thing is that if the denominator contains a prime number r other than 2 or 5, that is, now when we factorize the denominator q, the prime factorized form contains 2 and or 5, but it also contains r. Okay, if there is a prime number r other than 2 and 5, in the prime factorization of the denominator q, then it will be a non-terminating but repeating. One quick example that you can think of is that, let's say a equal to 1, b equal to 1, and c is also equal to 1, and let's imagine the smallest prime number other than 2 and 5, that will be, let's say, r equal to 3. Then what is q? 2 into 5 into r, that will be 2 into 5 10, 10 into 3 30, and let us assume p as 1. Okay, so p equal to 1 and q equal to 30, then p by q will be 1 by 30, and all of you take a moment and try to calculate 1 by 30. It will be a non-terminating but repeating decimal number. And if you look the other scenario, that is q equal to 2 into 5, again imagine a equal to 1, b equal to 1, so q is 2 into 5, okay, or nothing but 10, and again imagine p equal to 1, then p by q will be 1 by 10, and 1 by 10 you will see, observe that it will be ending into a decimal number which is terminating. Now let us take a moment and look at the value of square root of 3. Let us take a pause from whatever we are learning now. We will jump into a scenario of, or we will jump into the calculation of root 3. Okay, I am assuming that all of you know how to calculate the square root of a number. For now I will do it for 3. I will not go into details of how I have done. If you have doubt, you can take a pause and go through the process, or maybe write in comments. I will make a separate video in detail about how to calculate the square root of a number. For now, just observe and see. This process is not going to end. Okay, this will just go on forever, and here also it will go on forever. Now if I write more decimals without doing the actual calculation, you will get 1.73205008, and then again you will get 08, and it will just continue forever. Let us do one more example. Now let us look at the square root of 2. Again, I am not going to the details of how we are calculating it. I will quickly go through the actual calculation of root 2, but I will not dictate the step-by-step procedure. Again, similar to root 3, this will just go on, and this value will go on forever. Let me write some more digits over here. If you continue the calculation, you will get 1.414235, and then 62, and so on. Now from our calculations of root 2 and root 3, we observed that these values resulted into a decimal that is non-terminating and non-repeating, right? What was the value of root 2? Root 2 was something like 1.4142135562, and it is not going to end. So it is a non-terminating and non-repeating. Similarly, for root 3, we found out that the number came out to be 1.7320500808, so on. Again, it is a non-terminating and non-repeating scenario. We will look one more number, something like root 93. Again, you can see it is non-terminating and non-repeating. So by now you know that we got answer to one of our questions, that is there a decimal number that is neither terminating nor repeating, right? So this is the reason we took a detour from our lecture and tried to calculate the values of square root of 2 and 3, and now we know that yes, there are infinite decimals of the kind that it will be neither terminating nor repeating. Okay, so sometime back I showed you this particular number 4.35 and so on. This is nothing but the square root of 19. Okay, and now we move to the last question, that is, can we transform all decimals into the fractional form? So this is the reverse scenario. For most of the time in this lectures we were converting fractional form into the decimal form. Now we are looking, or we are asking that can we transform all the decimals into the fractional form. Okay, so for this we take the value of root 2. Okay, so root 2 we know the value is something like 1.42, sorry, 1.41 something, and now we take this decimal number and we will see that can we try to convert this into a fractional form. If any one of you is thinking that okay, root 2 is nothing but root 2 by 1 and thus a rational number, then take a moment and remind yourself this is wrong. Okay, what is a rational number? A rational number should be in the form of p by q, where p and q are integers. Okay, here root 2 is not an integer. So now we will make an attempt to find the fractional form of root 2. Okay, for this what we are going to do is that we will first assume, okay, or we will believe that root 2 is rational. Okay, we are going to believe that root 2 is a rational number such a way that root 2 is equal to p by q, and p and q are going to be a coprime. That means there is no common factor between p and q. Once more, p and q are coprime means there is no common factor between p and q other than 1. Okay, this is a very important thing to remember. So I can write root 2 equal to p by q as 2 equal to p square by q square. I am just simply squaring the both sides of the equation. Okay, now I can write as p square equal to 2q square. Now what I will do is that I will go into a series of steps trying to get a fractional form for 1.41, 42, 35, 62 and so on. So from this equation, p square equal to 2q square, okay, p square equal to 2q square, I can understand that p square will be a even number because p square is a multiple of 2. That means p square is even. P square is a multiple of 2, that means p square is even. And if p square is even, I can definitely write p equal to even. If you have any doubt, you imagine any even number that is a square. Let's say number 144. 12 square is going to be 144. That means that is 12 is a even number. If a square value is an even number, then its square root will definitely be a even number. And if p is an even number, then I can write p equal to 2k. Any doubt? If p is an even number, then definitely I can write p equal to 2k. K being any number. Whatever number we can imagine for p, we can always represent it as 2k. And if p equal to 2k, what I will do is that I will take this p equal to 2k and I will substitute here. Then I will get 2k whole square equal to 2q square. And I will do a quick rearranging. I will get 4k square equal to 2q square. Now 4k square equal to 2q square. This I can further reduce as q square equal to 2k square. Now if q square equal to 2k square, that means q square is even, and if q square is even, that means q is even, and if q is even, I can write q equal to 2t. The same way we got this. Okay, we got p square equal to 2q square, that means p square equal to even, that means p equal to even, that means p equal to 2k. Similarly, I got q square equal to 2k square, that means q square equal to even, that means q is even, that means q equal to 2t. Now what does this mean? This means that root 2 is equal to p by q, that is the starting point, and for p and q I'll substitute p equal to 2k and q equal to 2t. Okay, so I have root 2 is equal to p by q equaling 2k by 2t. We started our problem assuming that p and q are coprime, right? P and q are coprime. Now what we have just found out is that root 2 is equal to p by q, p and q are coprime, meaning there is no common factor between p and q other than 1. But what we have just got is that P by Q is equal to 2K by 2T, or 2 is a common factor between P and Q. Now, does it satisfy our original assumption of P and Q are coprime? No. So this is a contradiction. Okay, we end up reaching into a contradiction that P and Q is going to have a common factor. We started with the belief or assumption that there is no common factor for P and Q, but we end up with the result saying that P and Q have a common factor too. What does this mean? This means that our original assumption or belief was wrong. In other words, what this means is that we cannot represent root 2, okay, or root 2 cannot be represented as a fraction. So what was our question? Can we take any decimal number and convert it into a fractional form? And we just got a decimal number 1.41 and so on, and we understood that we cannot represent this in terms of a fractional form. Okay, so now we can answer the last question. Can we transform all decimals into a fractional form? The answer is no. We cannot transform all decimals into a fractions. Okay, if I summarize, this is what you can learn. Two important points which will summarize everything that you have learned now. That is, all fractions can be transformed into a decimal form. You take any fraction, you can transform it to a decimal form, and that decimal form will be either terminating or non-terminating repeating. It will be either terminating or non-terminating repeating. But all decimals cannot be transformed into a fractional form. Okay, just now we saw that a value of root 2 equal to 1.414 and so on, that is a decimal number, and we were not able to convert it into a fractional form, which means that there are decimals which cannot be converted into a fractional form.